Okay, so welcome back, everybody. Welcome to the afternoon session. And now we have a second talk of Eyvindur and Palsson about distance problems and their many variants.
Thank you, Giuseppe. And thank you again to Saurabh and Jotsaroop for the invitation and ICTS for the wonderful hospitality. So during my first lecture yesterday, we focused on distance problems and specifically the pattern of a distance. We saw the Erdős distance problem, the Falconer distance problem, the Matilda-Scheel invariant of containing a whole interval inside the distance set. And we saw some of the fundamental techniques that people have built on for some of the best results that have been established for these distance problems. Today, the goal was to look at some variants and specifically to move away from the distance and see what happens when we do that. So with that in mind, let's look again at the distance. So the distance takes in 2 points, and all it does is that it spits out a number. So it's just a function on 2 points. And we hope to generalize this in some way. And one very simple way of doing this is, for example, to look at triangles. What do triangles do? They take in 3 points, the 3 corners, and what do you spit out? You spit out the 3 side lengths. Okay. And why look at triangles? Well, it's a very natural geometric object. If you think about simplices, then you might think of the distance as being the simplest one, and triangle is the next most complicated one. Tetrahedron comes after that. So there are many natural reasons to look at triangles, but I will impress on you later on in the talk that, this is one example. You can look at whatever configuration you want, and there is no need necessarily to look at distance. Distances don't need to be part of it. You could do other things such as dot 2 vectors, calculate determinants of some inputs. There are all sorts of things you could do, okay? But we're just sticking to geometrically motivated things. So let's now note 3 inputs and 3 outputs. So we both change the number of inputs and outputs that come out of this. And you can ask, again, a very similar question to what Erdős asked. What is the least number of distinct triangles determined by endpoints in the plane? Now, of course, triples of points you should expect. Like if you just want to count triangles, then trying to get lots of them is easy. You should get about n cubed. And so the question is, how low can you go? Same as with Erdős distance problem. And here it turns out that you can go all the way down to n squared, but you can't go further than that. So for example, if you look at the regular n-gon, it's not too hard to look at all the triangles that are formed there, and you will see that there are about n squared, something like n squared over 12, and maybe there's a floor or a ceiling function there. Okay, so it can be computed very specifically. Okay, and in a wonderful result, Misha Rudniev took the tools the Guth and Katz used to resolve their distance problem in the plane and used them on triangles, but got all the way to n squared. There's no off by any kind of a logarithm. He slams on n squared. So to me, the problem is essentially closed there. Although, if you want to push a little bit harder, you could ask, well, what are the constants like? How close do you get? Those could be interesting questions. Okay, so that's kind of neat. Still a tiny little gap for distances, but triangles resolved. Okay. You may then ask, well, what happens in higher dimensions? And for distances, well, although the problem was not resolved, there existed some wonderful results. Here, there do exist some results, so maybe I'm a little overstating things here in the last bullet point, but really we are not very good at counting triangles in higher dimensions. And so I've done some of this myself, just played around with it. And if I just lay down a lattice and start counting, you can get a count. You get some sort of an estimate on how many triangles are in a lattice. But if you feed it into some of the mechanisms that I'm going to show you today, one gets things that are worse than trivial. And so I refuse to believe that the count that I've attempted is anywhere close to being true. And so I don't even know where to look. That is the scary part. Okay, I've actually worked with some very bright undergraduates that have looked at some of these questions in particular cases. What do the optimal sets look like? And objects that arise are the simplices. The octahedron arises as the object that has the fewest, that has the most number of points and only 2 distinct triangles. And so like there are these very regular objects that arise. So I think that there should be some sort of a lattice E or structure maybe, but certainly not the cube one. Okay, so I don't really know. And so like this is a thing that I love to tell people who like combinatorics, like what is the count? I don't know. Okay, so that's just a little bit on the discrete front. But of course, yesterday we moved quickly into the continuous setting. So I want to do the same today. Question?
Triangle means distinct up to rotations and.
Yeah, so we're thinking about congruence classes. Exactly, exactly.
It's the maximum of this triangle. I mean, if I just put all the points in the line.
And so, okay, good. So do you count degenerate triangles? And so when I want to count my triangles, I'm always going to be counting non-degenerate triangles. But this is a nuance to think about.
Okay.
Do you count them? And so these two things have to be kept clear. Yeah, that's a good question. Okay. And so really, if we now sort of copy sort of what we did yesterday, we created a distance set that encoded things. And so I'm going to do the same thing here. I'm just going to pull 3 points from a set, record the distances, and I'm going to call this the distance set. And yes, I know you're going to tell me that, okay, you know, what there are permutations may be involved, and I don't really care. That's up to sort of constant factors of counting or measuring things. So that's not too big of a deal. And so we can ask a similar type of a question that Falconer did. We can ask, how large does a set need to be so that we have lots of triangles? In other words, that the appropriate Lebesgue measure, that is the 3-dimensional Lebesgue measure of this is positive. Okay, so just a direct, immediate analog of Falconer's problem. Now, for triangles in the plane, because we're good at counting triangles in the plane, one can, in a very similar style as the sharpness result for the Falconer distance problem, come up with a sharpness result for triangles in the plane. So Erdogan and Josevich did this on the back of a napkin back in the day. So this is always cited as Erdogan and Josevich, back of a napkin. In one of the papers that I was involved in, we actually wrote this calculation out. And so 3/2. And so let me just note a difference here, that for the distance problem, the threshold is like d/2, right? So it's 1 for the distance problem. So this is strictly larger. So it seems like a strictly different problem, okay? So that's one observation. And let me say that the calculation that yields this 3/2 really is done on just a square lattice, okay? One of the reasons that that works out is that one gets slightly, one doesn't quite get the right count there. So like the regular n-gon was the right object with n squared. In the lattice, when you count, you're off by a logarithm. But these continuous methods, they don't see logarithmic terms. They only see powers on n. And for that sort of a reason, we get a nice threshold, okay? Because if I had to count this on the n-gons, I would not have liked that. One of the features of the lattices is when you scale them down, like they start overlapping if you take appropriate multiples of the same number, okay? Whereas for the n-gons, they don't really overlap in the same way. So that's kind of neat. But then, because we're bad at counting in higher dimensions, and that's where that kicks in, if I try to recreate exactly the same calculations that are done for this one in 3D and higher, and I count to the best of my ability, which maybe is poor, maybe that's just my fault, then I get thresholds that are worse than d/2. But let's just think about this. If there are lots of different triangles, surely there must be lots of distances. So the threshold for the Falconer distance problem surely has to hold for the triangles. The question is just, well, what you might expect is that the threshold should be higher. And I can't, because I can't count triangles. And so in higher dimensions, at least I know I can't dip below that. And so this is one of the urgent reasons why I would like to be able to count triangles better. Okay, so that sets the stage a little bit. Now you know, well, at least what to expect in the plane. I have some ideas of what could at least not happen in higher dimensions. What about positive results? So this first result really in the plane is due to Alan Greenleaf and Alex Josevich, and really was the paper that started it all. They were the first ones to really consider triangles back in the day. I followed up here with Lucas Grafagos and them, where we extended it into higher dimensions, and we obtained some sort of a threshold. And if you recall from the lecture yesterday, there were two main approaches that we had to the Falconer distance problem. It was sort of the L infinity approach, sort of the approach that gave the original Falconer's result of d over 2 plus a half. And so what we mimicked over here was that sort of an approach. Now you may pause for a second there, because yesterday I did a whole package together for distances. I did not only positive Lebesgue measure, but non-empty interior all in one fell sweep. So let me point out that over here, I'm only claiming that we have positive Lebesgue measure, not about non-empty interior. And I will come back to non-empty interior near the end of the talk. Okay. The next thing, the next set of results with Alan Greenleaf, Alex Josevich, and Bochen Liu is, well, improved dimensional thresholds. Especially good one in the plane, which has to do that we're able to use a mechanism of Tom Wolf's in there, whereas in higher dimensions, it just didn't yield anything for us. And so the conjecture is 3/2. We achieved 8/5, so that is strictly higher. So there still remains a gap, and maybe that is not too surprising when we can't solve the Falconer distance problem, that we can't solve this one. Okay. And this set over here was really through the L2 technique, and I'll show you sort of some glimpses of the proof of this near the end of the talk. I wanted to acknowledge that there are some more papers. So there's a fairly old one by Borg Erdogan, Derek Harton, and Alex Josevich, and then that was somewhat recently, like within the last year, improved upon by Alex Josevich, Fang Pham, Kui Pham, and Chunyun Chen. That achieves something that seems to that grows far better in the dimension than these previous results that I was showing you. What I do want to point out, though, is that if you look, say, just at the better of the results, in 2D, it's trivial. 3D, it's worse than the thresholds above. 4D, it finally matches it. It's only in 5D and higher. And so if you think about triangles are naturally living in the plane, and sort of the higher the dimensions, sort of the more degenerate they are within the dimension, then this is really just this is a high dimensional type of result. And the tools are very different. I've not shown you any tools that shed light on how they achieve this. This is through projection type techniques. Maybe I'll mention them at the end of the talk again, but different techniques. So, okay, so that is really the status. This is what we know for triangles. Ooh, and I should add maybe that at least this last result is also pinned. I may tell you at the end of the talk what a pinned result is. So it is stronger than just commenting on triangles. Okay. Now, yesterday I showed you some similar things, and then I walked through some of the proofs. And so in particular for this first type of a one, well, I could set up similar things. Like I could set up the triangle measure and do all those things. When I did this for distances, an important object that sort of emerged was the spherical averaging operator. And so what I want to do here is I just want to tell you, like, oh, the proof goes similarly for triangles. What is the object of interest? Well, it is something that I want to call the triangle averaging operator, an analog of the spherical averaging operator. And so I want to jump straight to that. And so the spherical averaging operator, it really was just about finding distance, really, because spheres encode distances. And so likewise, then this operator here is going to encode triangles. And so the way I think about it is that I'm looking at inputs U and V that form a particular triangle with the origin. Okay, and so if you wish, if you've determined particular side lengths that you're looking for, then say from the origin or from whatever your favorite point is, then you look at okay, U is supposed to sit at a certain distance, so it has to sit on a sphere around that point. When you have determined the U, then the V, where does that have to lie? Well, it has to lie on a sphere. It could be a different sphere, like the way I pictured it, they have the same side length, okay? It lies on a sphere, but it then has an extra condition, which is that it has to lie at a certain distance from you. So it doesn't lie on a full sphere, it lies on, well, like a circle within that, or a lower dimensional sphere. So the way I like to think about it, if U sits on a full sphere, then V sits sort of around it on a lower dimensional object, okay? And well, this is some sort of a manifold. So if you think about U comma V, that really the pair of them lives in R2D. You can think of their three equations, or really it's like a 2D minus 3 dimensional manifold. And then you can put a measure on this. You can normalize it. Things work very similarly as for the sphere. And why should this be the right object? Well, if you throw in, for example, indicator functions of a set for f and g, then morally this is counting the triangles that arise from points in that set. Okay. Now, objects like this have been studied before. So like these types of objects, so Bourgain did work on simplices. People have done this in a discrete setting, so I'm not necessarily saying that the idea is new, like as in much of mathematics, nothing is new under the sun, but I'm sort of more extracting it out for you. In terms of the continuous setting, really this emerged, like this was put forth and focused on as an operator, as an object by Alex Josevich and Alan Greenleaf, so that's really truly where the origin is in some sense. And for their first result, they needed results for this type of an operator. Diogo. I think of them as fixed for here, for now. Yes. Okay.
LP bounds for the triangle.
Sorry?
The LP bounds for the triangle averaging operator will have to.
That is true. And so if we think about it for the spherical averaging operator and sort of how that arose in the distance problem, then in some sense we froze the R. Okay. But then estimates, of course, dependent on the R, but we weren't very careful necessarily about saying a whole lot about that distance, about the R and how it arose. I can give you some idea of like why one doesn't need to care. So first of all, in the setting yesterday, we were dealing with a compact set. So we were never going to deal with infinite distances, so they were bounded from above. One can do a further reduction where one takes one set, splits it up so that you never need to consider the distance 0. You can bound it also from below. And so as soon as you have bounds from above and below, well, then you don't really care a whole lot. And so something similar happens over here, that we basically freeze the T1, T2, and T3. So I will probably set them all equal to 1 and just say, I'm going to look at an equilateral triangle and then try to prove results. Okay. Any further questions? No. Okay, so setup, very similar. And so let me point out that this is a multilinear operator, as in there are 2 inputs. You're linear in each of them, but you're not linear in them jointly. So this is a bilinear operator. Sometimes there's a little bit of criticism here that you could make, which is, well, I mean, you're working with one set. There's one measure mu that you put on it that sort of encodes the dimension, as yesterday. And just as with the spherical averaging operator, morally what we were averaging was that measure, or a smoothing out of it. You might say, well, these 2 functions really are the same. They're the same measure. Why are you encoding them with 2 different functions? Well, it turns out that most of the theorems can work with not taking all 3 points from the same set. You could take them from 3 different sets and still prove things. And in fact, like for the distance set, like that is actually valuable, because what I told you about wanting not to deal with the distance 0, well, it requires that you take your set, you pre-process it, split it into 2 parts. So really you work with the measure that you started with supported on 2 different sets. So actually being able to handle 2 different input functions is valuable. Now, okay, and so now you can see I've already just thrown out the t's and I'm working on the equilateral triangle averaging operator. Things are one, I don't want to track the dependence on the side lengths anymore. Okay, on the Fourier side, this is of convolution type. If you want to think about it, really this is like F tensor G convolved with the measure. So still a convolution type. And so if you're thinking about from the linear theory and how we worked with the spherical averaging operator, really we think it's properties of the measure here. The Fourier transform of this natural measure that should dictate what mapping properties you should have. Well, and then you look at them and you're like, oh, that does not look pretty. Sorry.
That is a function of this x, whereas Fourier transform is the.
Oh, yeah, okay, yes, so, it is true, I'm lying here, they're like, that should not look like that, yes. Sort of ignore that part, this is sort of morally what is happening over here, but yes, one has to be more careful, yes, this is a good point from Saurabh, absolutely. So ignore that part, think more about this one. This is sort of roughly what you should be thinking about what is happening there on the right-hand side, okay. So how does this measure behave? Well, Jotsaroop, they derived a very nice sort of strong decay estimate. So in the plane where Josevich and Greenleaf originally worked, there are some interesting things that happen. Let's go back to sort of the picture that I was thinking about. So when you're in the plane, and you're trying to build the triangle, okay, U has to be a unit distance from the origin. Okay, it lies on a unit circle. Where is V? Oh, and then you realize there's no lower dimensional sphere. It's either ahead by 60 degrees or behind. It is in very particular locations. This simplifies the operator quite a bit. It allows you to very explicitly write out what the measure is, and you can very explicitly calculate the Fourier transform here. And this is in the paper by Greenleaf and Josevich, and it's ugly, but lots of cosines and sines, but like you can really genuinely see precisely what it is. In higher dimensions, this gets harder because then you genuinely have a lower dimensional average. And so it was quite a feat that Josevich and Liu did when they calculated what is down here. Above one, I just threw in there, that was sort of not a refinement. It was like just a little observation on their calculations that I did with my PhD student, Sean Savine, where we just pointed out, like, if you look at this one here, you might be tempted to think that if this sine, so what is this? So there are two Fourier variables here. The angle here that shows up is the angle between them. And so if this angle is bad, you might be tempted to think that the whole thing disappears, okay? Or in other words, if this is bad, like it might seem like things might disappear, but that is going to be a rotation by pi over 3. So instead of having just psi plus eta, it's psi plus a rotation of eta.
Some axis?
Around some axis, yes.
Y-axis?
So I'm thinking just about the origin, and so eta. Oh yeah. Well, you have to specify an axis. So with respect, yeah, maybe the xi-axis. Yes. Yeah. The point, like, I really don't want to focus too much on this one because sort of the numerology is somewhat similar. Like, I think it's nicer maybe to look at this one here. And so if we focus on the upper one, then what happens is that if the angle between them is 0, then this first term is just 1. You get no decay out of it. The only decay you get is from the second part. Yeah. Let's just ignore this one. So I copied this almost straight out of there. Oh, theta. It is, okay. So psi and eta are two vectors.
If I'm taking in plane, then xi and eta both are real numbers, right?
No, they're vectors. We're in RD.
One if I'm taking, so this is RT and RT, right?
RD and RT.
Xi and eta are in R cross R, let's say in R2. Then how I am imagining 0 xi eta 0? Or
No, because I don't want to be an R cross R. Remember, the Falconer distance problem, don't want to be on the real line. So when I'm here, D is always bigger or equal to 2. It's the same as yesterday.
It's in the plane, right?
No, I can't be in the plane.
RD cross
RD,
greater or equal to
D greater or equal to 2. So the first one that I would ever look at is R4. So R2 cross R2.
first.
Yes. You're right. Like obviously in lower dimensions, this absolutely makes no sense whatsoever. Absolutely. And so if we focus on this one, so you can see if the angle between them is 0, then there's no extra push from here. You're only left with this one. And let me point out in dimension 2, then this would even disappear. What it means is that if you think about this symbol over here, there exists a direction when D is 2, which really means that we're working in R4 combined, right? There exists a direction where this just has no decay whatsoever, okay? And you might say, maybe your bounds are just bad, maybe there's decay and these bounds don't reflect it, but in the careful calculations that Greenleaf and Josevich did, you can really genuinely see it because they have explicit formulas for it, okay? So it's not just an artifact of the bound, that the bound is bad there, it is genuinely no decay in certain directions. And if you think about like the spherical averaging operator, I mean, this is devastating. Like one of the features of the spherical averaging operator is that there's decay. And like, there isn't really this question about directions anymore. Is either do you have decay or not? And generically in the linear theory, if you have no decay, it means that whatever you put in, the output is going to be no better than what you put in. Whereas the whole point with the spherical averaging operator was, well, we decay in all directions. What you put in, what came out was better than what came in. LP improving estimates and such, that was the driving force. And here, at least in 2D, we can see that there's no improvement in a direction. And the question is, how devastating is that? And then in higher dimensions, what this means is that, well, yes, then you start having decay in that direction, but it is less decay. So now all of a sudden it's not sort of symmetric, like some directions have more decay than others. How do you exploit that? How do you work that? All those types of things are interesting, and to me make this an interesting operator, which shows features that are different than in the linear theory. Okay, Diogo? So this one is not quite sharp. So if you count up the number of sides, like in the best types of directions, then over here, like what does it add up to? Like, it misses sort of this factor here. And so Josevich lose is slightly better because they have that factor in there. For our purposes, when we were calculating this, we didn't really care so much. We just wanted some decay and wanted to highlight that some directions have decay versus others. So one can squeeze a little bit. Do I think that this is optimal? I don't think anyone has proven that, but like, I would be surprised. Yeah. And in the good directions, this has about as good decay as you could hope for in some sense. And so it really is the vanishing in a certain direction, which is borne out in 2D explicitly. So like, I would think that this is quite tight.
This decay comes from short distance, or
Sorry, it comes from?
that U minus V is of mod 1.
Yes. Yeah. So, like you're saying, like if I actually wrote down side lengths, you might ask, how does this depend? And yeah, I certainly in the calculations that I did with Sean, we set everything as 1.
That's for some curvature problem.
Yeah. So they're like, if you have them and they would show up in here and how exactly, well, one could try to calculate, but yeah. Well, someone should do that. Yeah, John?
Yeah, I'm a bit confused about that.
Yeah, it's not the Fourier transform. Yeah. Ignore that part. Just focus on this one. It is taking this part and switch to the Fourier side. That was sort of like, ignore that.
Linear
You can
multiplied
say-
symbol.
Yeah. Exactly.
You take the inverse Fourier transform and restrict on the diagonal.
Yes.
Then that
Yeah. And that is sort of what I had in mind. Yes. Okay. Let me point out some other, so we've seen that this operator naturally arises when trying to study triangles. It is an averaging operator. It's multilinear. Multilinear thinks is something that people have been pushing towards, which is interesting. It has interesting features that you don't see in the linear theory, such as this different decay in different directions. There is yet another feature that is interesting about this. So I mentioned that, like, where is this supported? It's like 2D minus 3. And so if you go back to the linear theory, what kind of operators are well understood in the linear theory? Well, spherical averaging operators are well understood. So anything that is code dimension 1, lots and lots of work done in that setting. So quite well understood. Likewise, if you look at averaging operator along curves, so dimension 1, they are quite well understood. Intermediate ones, even in the linear theory, are not quite fully as well understood as the code dimension 1 and dimension 1 setting. So intermediate dimensions and or code dimensions, they are interesting and still being worked on, like some fantastic work by Phil Gressman and whatnot, but like not fully resolved. So that is yet another feature here that somehow we're intermediate dimension. And so one thing you could try to do if you wanted to say, like, okay, this is too hard of an operator, is that you could replace this thing here by, say, maybe a measure on a sphere where you say maybe u comma v lie on a sphere, and that gives rise to a model operator, the bilinear spherical averaging operator, that a number of people in here have worked on. Okay. Sorry.
We mean that if we take, let's say, instead of two functions,
yep,
I take a function in R2D and put it like x comma y minus u comma v. That is not known.
Oh, wait, you're trying to create a linear operator?
Linear.
So maybe I should be more careful. In the intermediate dimensions setting, I'm not necessarily, so there are lots of LP improving estimates and lots of estimates that are known in the intermediate. I think maybe what I should more carefully be saying is that there is even more known in the dimension 1 and code dimension setting. And so maybe I'm trying to say that the intermediate code dimension seems harder. Maybe it's less studied, but maybe harder is maybe the right word that I'm looking for.
But there are results for the linear one.
There are results, yes, yes. Like one can look at Phil Gressman, but like what exactly they would say for precisely that type of an operator, one would have to look at that, and then you have to make geometric assumptions and all that jazz. Yoko?
So this sigma,
Yeah.
that's a measure.
Yeah.
2D minus 3-dimensional.
Yes.
You say anything about the non-vanishing.
Not really in a certain sense. So, well, I have a feeling, so like if it were non-vanishing, right, you would expect that you would get same kind of decay as you would on the sphere, but like adapted maybe to this type of a setting, right? Maybe, or some numerology close to that. Like, yeah. Like let's look at these like 2D minus 4 over 2. Like it's like in the direction of maybe what you would hope, but honestly, like I've not looked at the geometry. Like to me, like curvature is just encoded in decay on the Fourier transform side. So when I look at the decay for the sphere, I go, oh yeah, non-vanishing curvature, right? And like I come at it from that end. So for me, like I just calculate the decay and then I say, okay, what's happening? And so yeah, that is an interesting geometry question. Right. Well, yes, and that would certainly. Like one of the things is that, yeah, there will be a different kind of a viewpoint on this, and maybe that will help you figure some things out. But this is sort of just blindly, like first look, you stare at the operator. This is how you would maybe try to go about things if you were trying to mimic exactly what happens for the sphere. Okay. So what happens then? What can you prove? You've cataloged sort of what properties you know about this operator. What can you prove? So yesterday, I began with maybe abundantly trivial observations about the spherical averaging operator. I told you that it mapped LP to LP for P between 1 and infinity and was absolutely trivial. And you might go, surely this must map LP cross LQ into LR with Hölder type exponents. Absolutely trivially. And yes, it does. as long as R is at least 1, because you can use Young's convolution inequality, and it just takes care of business because it's an averaging operator, similar type of a proof as you saw for the spherical. But when you are in the multilinear setting, you kind of would expect that you should be able to take P down to 1, Q down to 1, which would bring the R down to a half. And that breaks out of this regime. And all of a sudden, that is non-trivial. How do you get there? How do you go below L1? And so just using the Fourier decay, so being inspired by the abundance of papers in, say, Calderon-Sickman theory, multilinear Calderon-Sickman theory, you can just take your tools, your Fourier analysis, you can start decomposing on the Fourier side into annuli, cutting the annuli based on the angles because there was some difference in the amount of decay you got depending on which direction, and you can just grind through the calculations, and I did this with Sean Slavine, and we were able to push sort of beyond what you would expect. So this is sort of a Riesz diagram. These are the inputs, so this is 1 over P, this is 1 over Q, so you should think about like L1 is at the, like L1 cross L infinity is sort of sitting up at these things, L infinity cross L infinity is over here. This sort of line corresponds to R equals 1. And sort of the goal is to push all the way out over here and sort of complete the rectangle. That's the goal. And so in this first sort of attempt where you just use Fourier type of techniques, we're able to show that, well, yes, you can push. We're able to get out there a little bit. And so that was sort of proof of concept that yes, but it left a lot to be desired. Not only in terms of like dimensional thresholds, but like it didn't push very far. And so maybe one of the things that it points towards is that it would be really exciting to see better development on the Fourier analysis side. How do you handle multilinear geometric averaging operators? And that is just not very well developed at all. Okay. Now, there is an important viewpoint. So the way I've described things so far really tracks what you saw with the spherical averaging, but there is more geometry here, which has been implicit in sort of what I've been telling you. The way I've been describing how you pick your triangle, this idea that if you pick one of the variables first, it lies on a sphere, and then the other one lies on a lower dimensional sphere, you can actually make this accurate. You can show, using proper measure theory, that you can break the measure down into 2 parts, where this d sigma view is just your genuine spherical averaging, the same one that showed up yesterday, and the other one is then going to be analogous spherical average, but on a lower dimensional sphere that depends on the U, which is basically this picture that I've been drawing with my hands, which is like as soon as you've chosen U, then V has to lie on a lower dimensional sphere away from it because it has to be at a unit distance from the origin, as well as being a unit distance from U. And so you can genuinely actually do this. Now, this sort of viewpoint is due to Brian Cook, my colleague, Neil Lyle and Akush Magyar. And this sort of viewpoint was very crucial. They actually were working originally in the discrete setting, and I think that's sort of where the idea came from, and that implemented it. And one of the things that this allows you to do with some very clever, either Hölder or Cauchy-Schwarzing, is that it allows you to kill the inner average and dominate the operator pointwise by spherical averages of powers of the input functions. And you just get pointwise domination, but it is of spherical averages of the powers. And although this seems simplistic, this yields quite some mileage. And if you apply this, you get to push far further out. So almost an embarrassment for Fourier analytic techniques. And what I do not understand is whether the structure here is so special that you get these things, and so Fourier analytic techniques should not be embarrassed, or is it that we are wielding them incorrectly? And so any kind of understanding of that, deeper understanding of that, would be nice. And this is with Alex Josevich and my PhD student, Sham Sami. And you can see the threshold, sort of like how far did we push out? So we didn't quite manage to push out to the full rectangle. So the point out here, like that would be far out, would be correspond to L1 cross L1 into L half. So we don't quite get to go down to L1. We get to go down to LD plus 1 over D. So in the limit, we're getting like closer and closer to filling out the rectangle, but for any particular D, we don't quite make it. So there's a gap there that's still open. And so it'd be very interesting to see what happens. Just to say a tiny little bit of word about how do you prove this? It's slightly more complicated than just taking Helder. So taking Helder, what it allows you to do is it allows you to prove LP improving estimates into L1. And then you can take a technology that I learned from Lucas Grafakos and Nigel Calton that allows you to take LP improving estimates into L1 and leverage them into these type of Helder estimates that go below L1. That's really where this point comes from. And so it's maybe yet another theme that matches a little bit with Michael's lecture yesterday, which is LP improving estimates. You can take them and leverage them in various different directions. Maximal ones, sparse ones, and here's another example, getting LP estimates below L1.
Can you repeat this pointwise dominance?
Yeah, the pointwise domination is by a product of spherical averages of powers of these functions, and then there are sort of roots that are included. And so like
Spherical function acting on some power of
yeah, it's the spherical average of these functions. So it's like S of F, but it's a power of F. So it's like S of F to some power, and then there's some root on that. And then there's S of G to some power and some root on that. Like there's some homogeneity there. So what are these LP improving estimates? Well, as I mentioned, in 2D, this operator is far easier because it's essentially an average along a curve, because as soon as you've chosen one of the points, the other one has only two locations to be. So it's kind of like a curve average. Curve averages have been done for a while, appear, for example, in Betsy Stovall's thesis, like a large range of estimates. Now, granted, they're set up in a very broad way, so it takes a while to check all the conditions. One can also do this just directly for the operator, and that's something that Alan Greenleaf, Alex Josevich, Ben Krause, and Alan Liu. This is not Bochen Liu, this is Alan Liu. But Ben, I think, is speaking later in the week. They did this just by hand directly and obtained basically sharp estimates for the triangle averaging operator in the plane, which again is not surprising because it's kind of degenerate, if you wish, there. And so they got LP improving estimates into L1. They got this L2 cross L2 into L2 restricted strong type. Then, of course, you know the Helder type of estimates, at least down to L1. And you can interpolate, and this gives like a wide range. Now, granted, they never dipped below L1, so that was sort of left to the side. But certainly in the Banach range, that gave sort of a full picture, except perhaps at this endpoint. And so there's maybe some interest in sort of making sure that this endpoint is okay. I've talked to Betsy a little bit about this, and she thought it might be interpretable from some other works, maybe Tony Carberry, Jim Wright, some of them. But it would be nice to check this, make sure that one can actually remove the restricted strong time and just say that it is a full-on endpoint estimate. That would be nice. And so with Alex Josevich and Jean Samin, we did some analog of this. So we had LP improving estimates into L1. And so here's the D plus 1 over D, the one that showed up on the previous slide. That's where it sort of comes from. This is the bound that we leveraged for these this wider range of bounds before. And this is sharp. This is like, well, at least in higher dimensions, this is one of the few things that I know is sharp. Okay. We could also mimic and get the L2 estimates, and then using this domination by spherical averages, we could push far higher, and one could interpolate and get some estimates. But do I think that these things are sharp? And the answer is no, I do not think that they're sharp. And so I advertise for, could anyone try to get better LP improving estimates for the triangle averaging operator beyond sort of this? Maybe you're wondering, what is this M that shows up? The M you should think of as it's like half the dimension is like D over 2. I'm using notation from Cook, Lyle, and Magyar here. And so, yeah, that gives you some idea of what the LP improving is. Like, if this is around LD, this is around LD, and this is around LD squared. So like the amount of LP improving is on the order of D. It's quite good, but I don't think it's sharp. Okay. Now, one can of course also look at maximal operators. And so here I look at a sort of simple version where I scale up just the equilateral triangle. So you could think of this as a maximal equilateral triangle. So an analog to the maximal spherical averaging operator. You could ask, how does it map? Well, you expect sort of Hölder type mapping properties. And it's very trivial to do this if one of the input spaces is L infinity, because then basically all you have in front of you is a spherical averaging operator. So you get a wide range sort of immediately for free that is within the Banach range, but can you push further? And we conjectured that you could go all the way down to some estimates of this type, maybe restricted sort of estimates of this type. And this was sort of based on the fact that for the spherical, maximal spherical, you can only go down to D over D minus 1. So that sort of puts a limit on what you can do here if one of the functions is an L infinity. That sort of is where our conjecture came from. It's not that we had necessarily a function outside it that blew up. And there's been progress on this. So Kuklai-Elmacher, with her pointwise domination, that's sort of where it originated from, managed to obtain results of this type. Again, think about M as being half the dimension. And so the point is that these thresholds here out front are something that go to 1. So in the limit as D goes to infinity, they get sort of sharp results. But for any particular dimension, they're off. So again, refining this, seeing how far could you go where it's not just simply dominated by linear operators, that would be very interesting. There are also some sparse bounds that I did with Sean that built on the work of Saurabh and where are you, Kalashant? Yeah, there you are. Very good. Okay, so they had some wonderful work where they worked on products, bilinear products, spherical averaging operator, and so we leveraged some of that and did some of this for the triangle averaging operator. And so this connects again to Michael's talk that sparse bounds are interesting, maybe can be leveraged into fun things. And really maybe Michael understated even yesterday. So his paper on the sparse bounds for the spherical averaging operator really were the first sparse bounds for a geometric averaging operator. Sparse bounds had existed in the singular integral world, but it's not trivial. You can't just jump from singular to geometric averaging. And so it was a very important paper that he had there that then, as you can see, many people have built upon. Okay. Then a little ad for a talk that happens tomorrow. The last talk tomorrow is my collaborator, Tess Anderson. And so because you've been seeing discrete operators this morning from Michael, one can also look at discrete analogs of these things where you, again, look at U and V that form some sort of a triangle, but you start restricting to an integer lattice setting, and then you average by counting the number of triangles. And so this is going to be very similar to a spherical averaging operator that Michael may or may not show you in the discrete setting. And he talked about, well, for the spherical averaging operator in the discrete setting, you need to be at least in dimension 5. So you have like a regular count, so you have enough points. For us, you have to be in a high enough dimension so that this variety has enough integer points on them. In fact, you have to be in dimension at least, well, you have to be in dimension at least 7, but our results are only in dimension 9. And we get some sort of LP cross LQ into LR results using sort of heavy-duty number theory, sort of analogous to what Michael is introducing to you. So this was just a tiny little flash. I didn't want to say anything more. Tess is going to go into far more details on these things, but I just wanted to say that there's a connection to what Michael does, and you'll see more of it tomorrow. And Tess, if you're watching, sorry for stealing your thunder. And then some of our results have been complemented by the results of Kuklai-Elmacher. This is actually where they started. So I find it really fun sort of that some people are working in the discrete, some in the continuous, and there's swapping between some ideas show up more naturally in discrete. So they feed one another. So it's not like that we're just busy working all different directions. They all sort of blend and help one another, eventually furthering our understanding of these objects. Okay. So that was a little bit on multilinear geometric averaging operators. Could have done another 30 minutes talking about like the more model operator, the bilinear spherical, but I wanted just to stick to triangles because that's sort of what I'm motivated. One can look at simplex operators that correspond to simplicity. Like there's a whole lot of stuff to look at here, but this was sort of an example of a storyline. So what I wanted to do now was that I wanted to come a little bit back to the geometric measure theory and tell you just a little bit more about what's happening there with triangles. So recall the Mattila-Sherlin theorem from yesterday, which was about if you look at the distance set, then you can ask, does it contain a whole interval? And that was sort of a stronger result than just saying that it had positive Lebesgue measure. And so we talked about yesterday and even sort of showed a proof of like how if you're above the threshold d+1/2, then indeed you can show that this distance set has non-empty interior. It contains an interval. Okay. Well, I've not shown you anything like this for triangles. And so it's a very natural question then to ask, okay, you've shown us results that shows positivity of the triangle set. What about non-empty interior? Can you do some of that? And what it boils down to, if you think about the proof that you saw yesterday, if you were here yesterday, it really boiled down to being able to explicitly compute the density, seeing the dependence on the distance, and understanding that the density you were working with was continuous there. And sort of as it's been pointed out with the decay estimates that I gave you, wow, I didn't write them out for general things, and one can start working, but like the decay is hard to work with. Like, what is the density exactly? How? And that gets hard, and I don't know how to handle it, which is why you haven't seen any kind of non-empty interior type of statements so far. Now, we have been talking about distances and triangles, and so I hinted at or maybe earlier in the talk that one can look at all sorts of other configurations, angles, chains, all sorts of things. And sort of generically, we think about them as you just tell me how many points go into the configuration. If there are k+1 points that go in, I talk about it as a k configuration. So like for distance, my k is 1 because there are 2 points that go into it. And sort of it corresponds to there's one link. So it's about the number of edges in the graph, not necessarily the number of vertices in some sense. And so like, wow, maybe that's bad. This is k = 2 for the triangles, etc. 3 points here, so yeah. In any case, Alan Greenlee, Alex Joseph, and Crystal Taylor, they have done Mattila-Sherlin type theorems for various k-point configurations. Okay, here's one example. The quantity that I've written down here, the configuration that it corresponds to, it takes in 3 points. These you could think of as sort of side lengths of the triangle that they form, and what you're computing here is the area of the triangle. And you can ask, how large does the Hausdorff dimension of my set need to be such that the set that contains areas of triangles has non-empty interior? And they found out a threshold for that. And this is just like one example that is lifted quickly out of their paper without thinking a whole lot about it. They have sort of a general scheme that if you have some sort of a function here that takes in points and if it has certain properties, then you can get these Mattila-Sherlin type theorems. But what is interesting is that their method did not originally work on triangles. And their method I wrote here, FIO, is a Fourier integral operator method, or maybe more appropriately, they're using microlocal analysis, which of course is very sort of tied into the harmonic analysis, sort of good buddies. And so one of the things was that this motivated this question, so what happens for triangles? Can you get a Mattila-Sherlin theorem? Because it does exist for lots of other configurations, what happens? And with my PhD student, Francisco Romero Costa, we were able to obtain a non-trivial threshold, 2/3 d+1 in dimensions 4 and higher. We were able to see that this set had non-empty interior. So you might go, well, how did you do that? Well, this is an example where, yeah, sure, we had worked on the triangle averaging operators, but we don't understand them well. So we went back to the geometric measure theory and we went like, how can we change things? And we changed things a lot, although they seem elementary. I was encoding triangles with side, side, side. Well, you can just as well do side, angle, side from elementary geometry. And that viewpoint helped us. Working with angles, though, is really scary because it's hard to encode them. If you just tell me 3 points, what's the angle? I mean, everyone can tell me what the cosine is, but I need to know the sine too. And so working with angles is something that scares me, but we still were able to sort of get around it. I will say our techniques, though, they blow up at certain angles, like 90 degrees. And it, like, sometimes right angles behave differently than other angles, but the blow up that happens is absolutely irreparable. And so there are bad things that happen. And the only reason why we survived was that we were able to pre-process our set and avoid entirely right angles. That's why our proofs worked out. And we had to build on some heavy machinery of Josevich and Liu, where they were showing existence of equilateral triangles, a related type of a problem. Okay, so lots of interesting sort of calculations going on. Now later on, Alan Greenlee, Alice Joseph, and Kristen Taylor were able to take their microlocal analysis technique and not refine it once, but twice, and were then finally able to match. So they didn't get any better, but they matched our threshold and matched our dimensional threshold, managed to achieve the same result through that refined machinery. But it still leaves question like, can you do better? What is sharp? Can you improve the dimensional threshold? And so we were able to push that a little bit further with Francisco. There we were able to go back to the side, but we did something that would be atrocious to do for the triangle averaging operator. We took out one of the quantities just by L infinity. We took a massive loss on that, but remarkably, it allowed us to get results in low dimensions, but our results are absolutely atrocious in higher dimensions, which is why I didn't write them. But it allowed us in dimension 3 to squeeze down to a non-trivial threshold. Note that this is less than 24/8. So it's a non-trivial threshold. So we managed to make it there. And this has not been matched by the microlocal analysis technique. So there exists this sort of question, how far can you push the microlocal analysis technique? Is there any hope of getting down to 2D? It would be interesting if you couldn't go down to 2D. Can you improve these results? Okay. And so what you see here is that these are very sort of ad hoc type of methods. And so one of the goals with the whole program is like, if you understood the triangle averaging operator better, maybe you could mimic the proofs I showed you yesterday and do just in one fell sweep, non-empty interior, positive Lebesgue measure above a certain threshold, and not have to do this gymnastics to squeeze out results. Okay, and our results extend to simplicities in higher dimensions. We can do tetrahedra, and there are all sorts of other things you can do. So I promised a little bit yesterday, so let me quickly show you one more thing and then I'll finish. Any questions before I do that? Okay, so what I wanted to show you was that yesterday we did, we went through the L2 method, the one proposed by Mattila, the one that has produced all the best results for the Falcon distance problem. And you could say, the techniques that we have used for the triangle so far, like how do they work when using that L2 technique? Well, we do the same things that we did yesterday. We encode the dimension of the set with some measure mu. We create a push forward measure. Yesterday we pushed forward just under distance. Now it's a push forward under the actual triangle of the 3 side lengths. And you do the same thing. You want to show that this has density and set density is in L2. It's bounded in L2. It is exactly the same thing we did yesterday. Yesterday, the trick was write out the square as an integral along on a diagonal. We do the same thing. And what this then encodes is that 2 triangles are the same. Well, if 2 triangles are the same, it means you can rotate one into the other. It's exactly the same principle as we saw yesterday. If you then calculate this appropriately, one can dominate this square by where you've input these features that we saw yesterday. It's kind of similar. Now it just happens in 3 of the coordinates. This happened yesterday in just the 2 that you had. Now it happens in all 3. And you have been allowed to throw in an extra rotation. And what I'm going to do now is I'm going to say this is some sort of an invariant that happens for sort of pairs at a time. And so I'm going to encode it with a special measure that I'm going to encode d mu sub g. And what it encodes is sort of this feature here, as in I'm going to take this element minus g times another element. I'm going to encode, I'm going to block them together 2 and 2 at a time. And so I had 6 measures over here. So when I block them together, I end up with 3 of them. Okay. Now, if you look just at the definition, if you plug in for the function here, this is just a definitional definition really. So if you plug in e to the 2 pi I, if you try to take the Fourier transform, this splits and you exactly get a product of 2 Fourier transforms. Now, if we start estimating this and I do the dumbest thing possible, I pull out by L infinity so that I'm left with a square and I go to the Fourier side, well, with Planck-Chervel, if I plug in 2 of these, it gives you exactly the expression that you see over here. This is exactly the expression that we saw yesterday. This is exactly the Matilda integral. And when you do this, you can get a result. This is how you prove the threshold, the 8/5 thresholds that we have for triangles in the plane, the best one that still exists. And what happens really is you take a loss here. You have the same sort of numerology as for distance over here. And so the point is, when you balance the loss with the distance thing, you should get a threshold that is worse than for distances. And yeah, that's exactly what we do. But yesterday I sort of mentioned that like there exists these analogs of the Matilda integral. And so to me, this thing here is a generalized Matilda integral that does not let you go by Planck-Chervel immediately to the L2. So it would be really nice if someone could do this in a smarter way. And I can tell you so that 3 here comes from triangles. If you look at higher order simplices, it just increases the power here. So one trick you could think of is doing the tetrahedron at power 4 and get to a convolution of some things. And so that is what some people in here know about, pointing at you, Diogo. And that could be very cool to try to establish, and connections with restriction and stuff like that. And so that's the question. But I think that's a great place to stop. So again, I'm not going to do these last 2 slides, same as yesterday. I think this is a perfect place to stop. So thank you.
David, great talk. So are there any questions or comments? So as an icebreaker, I have a simple-minded one. Of course, can you go back to the previous slide? These 4, these 3, the last one you showed us.
Oh, yeah. This one here.
So how to force this exponent 4? Would it be considering other figures other than triangles?
Yes, so you're asking if there was a 4 here?
Yes.
That would be the tetrahedron.
The tetrahedron.
Yeah.
Okay.
And so a genuine geometric,
Yes,
but like it would be a
absolutely.
step towards trying to understand these things better.
So you think the tetrahedron could be better behaved and more understandable than triangles?
Possibly.
Possibly. That would be cool.
Like, but I can't say like, I mean, I've tiny little bit looked at it, but not very seriously. But
Yes.
like, it's still rough. I mean, sometimes even natural powers, they're often nice. And I should say maybe like this group action stuff I showed you here for triangles, this is really where it was discovered. And so the point is, would we ever have come up with this rotation business if we had just been looking at distances? Well, nobody had up until that point. And so it was, so sometimes like there's this question, why do you look at harder things like triangles when distances are still to be understood? And that's because sometimes when you look at more complicated things, you can get motivated and realize that there are tools that are maybe too trivial to think about in the simpler setting that you can then bring back. And this is a prime example of that.
Yes. Fantastic answer. Further questions?
I noticed that some of your results start working in high dimensions like d greater than or equal to 7 or d greater than or equal to 9.
Yep.
Is it just because of Fourier decay that's not available?
Yes, precisely.
Okay. Thanks.
And that is exactly also what happens with the thresholds in the Matilda-Schilling theorem. Like we can show that the density, using the decay, that the density is bounded, the thresholds that we have depend on these decays, and yeah, then we get stuck.
Other questions from the online community? No questions. Okay, so let's thank Avi again.